Hello everyone, good morning. I think I'm audible, right? Yes, good morning. So this is lecture number 2 of modern algebra. So if you haven't watched the previous video, so please watch the previous video and come back to this video, right? Because this is the continuation of the previous class. So the previous class, what we did is we have introduced the definition of group, and then we have seen 13 examples for an infinite group and 4 examples for finite group, right? So overall, we have seen almost 17 examples as of now. The first 13 examples are an example of an infinite groups. That is, we have checked whether it is group or not, right? And then we have seen 4 examples for finite group. So we have seen overall 17 examples. In some examples, it forms a group. In some examples, it doesn't even satisfies the definition of closure property, like the set of all irrationals with respect to multiplication and addition, right? Yes, so we will continue. I'm going to continue giving more examples. So we'll start with example 18, right? So in the previous class, I think we have stopped at, I have given 17 examples, 13 for infinite, 13 for infinite set, and 4 for finite set. So we will start with example number 18. I'll give you some more examples. After that, we will do problems based on groups, right? The problem will be like, they will give a set, they will give a binary operation. You need to check whether it forms a group or not, right? So first I'll give you more examples for groups. After that, we will solve problems based on groups, right? This is what we're going to do in this class. Okay, so we'll start with example number 18, right? You just have to understand all these examples, right? So if you understand all these examples, then everything will be very easy for you to follow, right? The next remaining concepts all are okay. Example 18, the set the set of all the set of all m by n matrices, the set of all m by n matrices over, so it can be irrational or it can be real number or it can be complex number. Over means the entries in the matrix can be rational or it can be real or it can be complex number also, right? Over means the entries you will insert in matrix, right? That aij element. The element can be q or it can be r, it can be c, it can be anything. The set of all m by n matrices over this forms an abelian group. It is infinite, right? Forms an infinite abelian group. This infinite abelian group under matrix addition. The operation is matrix addition. That matrix addition, right? The operation is whenever you are having two matrices, A star B is A plus B, and A plus B is nothing but the usual addition of matrix, right? So you can easily prove this. So it is closed, right? Because sum of two matrices again a matrix, right? Sum of two matrices again matrix. Sorry, this n by n matrix. Um, Closed, and it is associative also, right? So matrix multiplication is always associative, right? Matrix addition is always associative. And what about the ID element? What about the ID element? Zero matrix will serve as our ID element, because if you add any matrix to zero matrix, you will get that matrix back again. So zero matrix, right? ON. So zero matrix of order n, right? Zero matrix of order n. 0, 0, 0. So zero matrix of order n is an ID element for this group, right? And what about the inverse? For A belongs to set of all m cross n matrix minus A is the inverse. Minus A is the inverse, right? For example, if you take A to be equal to 2, 3, 4, 2, what will be the inverse for this under addition? So you need to add one more matrix to get this as 0 matrix. So that means this matrix has to be what? Minus of that matrix. Yes or no? So minus of that matrix will give you 0 matrix. So for any matrix, minus of A is the inverse. And also commutative also. And also it is commutative also because for A comma B belongs to G. You take any two matrix in G, then A plus B is same as B plus A. A plus B is same as B plus A. Remember, this A plus B is nothing but you are adding the entries in real number. For real number, A plus B is same as B plus A. So that means it is true for this also. So therefore, it forms an infinite abelian group under addition. Is it clear? Set of all n cross n matrices, a set of all n cross n matrices forms an infinite abelian group under matrix addition. The entries can be Q or R or it can be C also. What about under multiplication? Is it a group or not? In the previous class, we have defined what is meant by group, right? Group means it has to be closed, associative. There should exist an ID element such that A star E is equal to E star A is equal to A. For inverse, for every A, there should exist A inverse such that A star A inverse has to give you ID element. If it is commutative means it will be abelian group also. So what about if my operation is multiplication? Is it a group or not? Just think about it, right? The same thing, if the operation is instead of matrix addition, what happens if matrix multiplication? Is it a group or not? Example 19. The set of all the set of all n cross n matrices over, see, it can be over real, it can be R, Q or C also over real number under matrix multiplication. Under matrix multiplication does not form a group. Why? Does not form a group. Why? Why it does not form a group? Under multiplication does not form a group. See, for closed it is easy, right? Because product of two matrix is again n cross n matrix. Product of two n cross n matrix again n cross n matrices. It is associative also. Matrix multiplication is always associative, right? What about the ID element? The ID matrix will serve as the ID element if your operation is multiplication. ID matrix will serve as your ID element because if you multiply any matrix with ID matrix, you will have that matrix back again, right? This is your ID element. What about inverse? Inverse does not exist for all matrix, right? Inverse exists for a matrix whose determinant is non-zero. If you have a matrix whose determinant is zero, A inverse does not exist, right? For example, if you take A to be equal to 2, 3, 4, 6, right? 2, 3, 4, 6. Now what about determinant of A? Determinant of A is 0. That means what? A is singular matrix. So if you have a singular matrix, A inverse does not exist, yes or no? So A inverse exists only for non-zero determinant. That is A inverse is 1 by determinant of A into adjoint of A. So there are many matrix whose determinant is 0. So for all those matrix, inverse does not exist. That means it fails the condition of inverse. It is also not commutative also. Matrix multiplication is not commutative. AB is not equal to BA for matrix, right? Okay, so that means doesn't form a group. See, it is monoid because it is closed associative and it has ID element. I'm going fast. See, I'm assuming that you have watched the previous class. You have watched the previous class, and you can easily follow, right? If I'm going fast, just make a comment. Okay. Yes, Shashanka, I will do that, right? I will do in the upcoming classes. First, we will cover the basics. Okay. So that means it doesn't form a group because inverse does not exist for all element. Okay. Now, what I'm going to do is, see, if I remove all those matrices, okay. If I take only a matrix whose determinant is non-zero, then it will form a group. Yes or no? See, this consists of all n-cross-n matrices. Here I am saying that I have a matrix whose determinant is 0, so therefore for this matrix inverse does not exist. What happens if I take a matrix which has non-zero determinant? Then it will be a group under matrix multiplication. Yes or no? If I collect all those matrices whose determinant is not equal to 0, then it will form a group because the one whose determinant is 0 is the one that is troubling us. If I remove all those matrices whose determinant is 0, then we will have a new set. That new set consists of all those matrices, n cross n matrices, whose determinant is non-zero. Then that set will form a group under matrix multiplication, right? So for if you want matrix n cross n matrix to be a group under matrix multiplication, normal all those n cross n matrix will not form a group because in n cross n matrix there may be a matrix whose determinant is 0. But if you collect all those matrix whose determinant is non-zero, then it will form a group under matrix multiplication. That group is called GLN, R. Right? GLN, R. So it means general linear group. So all those n by n matrices, right? It is called all n cross n non-singular matrix. All n cross n non-singular matrix. That is, this set consists of all those n by n matrices whose determinant is non-zero. It consists of all 2 by 2. If you put n to be equal to 2, all 2 by 2 matrix whose determinant is non-zero. If you put n to be equal to 3, all 3 by 3 matrix whose determinant is non-zero. If you take n to be equal to 4, all 4 by 4 matrix or 4 by 4 matrix, uh, all 4 by 4 matrix whose determinant is non-zero. So it is called general linear group. It's called general linear group, right? So if I write this in mathematical term, so it consists of all those n cross n matrix as it is equal to A. It consists of all those A in n cross n matrices over real number. See, this is the notation for set of all m by n matrices over real number such that determinant of A is not equal to 0. So you collect all those n cross n matrix whose determinant is non-zero. This is called GLN, R. If you fix n, you have to fix n at the beginning itself. If you fix n to be equal to 2, you are collecting all those 2 by 2 matrix whose determinant is not equal to 0. If you fix n to be equal to 3, you are collecting all 3. It's an infinite group. It is an infinite group because there are infinitely many matrix of order 3 whose determinant is not equal to 0, right? Okay. So you can see it is closed, right? You can see it is closed. Why? You take any two matrix, you take any two matrix in GL, N, R, right? So you need to show A star B is also here. So what is A star B? It is nothing but matrix multiplication. Now what about determinant of AB? So determinant of AB is same as determinant of A, determinant of B. The determinant of A is not equal to 0 because A belongs to GL, N, R. That means what? So both the determinants are not equal to 0 by assumption, right? Because we are collecting two matrices in GLN, R. GLN, R consists of all those non-singular matrices only. So that means determinant of AB is same as determinant of A, determinant of B. So both are non-zero. So that means determinant of AB is also not equal to 0. That means if this determinant is not equal to 0, then AB belongs to GLN, R. So it is closed. Or no? So I am taking two elements in this set. I need to show A star B is also in G. A star B will be in G if the determinant of AB is not equal to 0. Determinant of AB is same as determinant of A to determinant of B, and determinant of AB both are non-zero because AB belongs to this set. So that means it is closed. And associative, it is associative, right? So you just write matrix multiplication is always associative. Matrix multiplication is always associative, right? Okay. And what about the ID element? Again, here the ID matrix will serve as an ID element, right? So IN is the ID element. So ID matrix of order n. And what about the inverse? What about the inverse? For A belongs to G, or A belongs to G. So A inverse is nothing but 1 by determinant of A into adjoint of A. This you already know, right? So since determinant of A is not equal to 0, inverse exists for all A. So this is the inverse. This matrix will be the inverse for that matrix. And what about commutative? It is not commutative. Matrix multiplication need not be commutative, right? So AB is not equal to BA in general. These are very elementary, right? Matrix multiplication need not be commutative. You just take any 2 by 2 matrix. You just take any 2 by 2 matrix. You just perform AB and BA. It need not be equal in all the times, right? So it doesn't form an abelian group, but it forms a group because it is not commutative. So it forms a group. It forms a group, but not abelian. But not abelian, right? So we have seen 3 examples. The first example is all those n by n matrices under addition forms an abelian group, and n, and in here matrix multiplication, all those n by n matrices will not form a group under matrix multiplication. But if you collect all those matrices whose determinant is not equal to 0, then that will form a group under matrix multiplication. But doesn't form an abelian group. So example 21. See here, I'm writing GL n comma R. Now I'm going to denote one more group that is called SL n comma R. Right? So this consists of here all those n by n non-singular matrix. So here we will have all n cross n matrix whose determinant is 1. Whose determinant is 1. So I'm collecting see here also you will have all those determinant not equal to 0. But that means determinant can be 2, it can be 3, it can be 4, it can be 5, it can be minus 100, or it can be 1000, anything. Here I am collecting all those matrix whose determinant is 1. Then this set will also forms a group. It is called special linear group. It is called special linear group. See, this is a subset of GLN comma R. Yes or no? SLN comma R is a subset of GLN comma R. Because this group is also in that all these elements in this group will also be here also, because this consists of all those matrices whose determinant is not equal to 0. Here is a special case, so this is a subset. So SL n comma R is contained in GL n comma R, right? And this is contained in all those n cross n matrix. This is contained in all those m cross n matrix over real. You just understand these 3 relations, right? This is contained in all those m by n matrices. Okay. This is a subset of m cross n matrices over real numbers. Yes or no? This is a subset of this. This is a subset. Okay. Here consists of, so what is SL n comma R? So it consists of all those matrix Aij all those n cross n matrix such that determinant of A is equal to 1. Right? In the previous case, determinant of A is not equal to 0, but here determinant of A is 1. So again, it is closed. Right? Because you take any two element in SL n comma R. Right? So what about A star B? A star B is AB because it is usual matrix multiplication. Forms and with respect to matrix multiplication. See, what about determinant of AB? It is determinant of A, determinant of B. So both are equal to 1 only because AB belongs to this. That means determinant of A is also 1, determinant of B is also 1. So that means determinant of AB is 1. That means AB belongs to SL comma. And it is always matrix multiplication is always associative. Matrix multiplication is always associative. And what about ID element? Again, In is our ID element. Identity matrix determinant is 1. Right? So that means it will be an ID element. And what about the inverse? So A inverse is 1 by determinant of A into adjoint of A. And since determinant of A is equal to 1, so it will be 1 by 1 into adjoint of A. So adjoint of A. So A inverse is nothing but adjoint of A. Right? So for every A inverse is adjoint of A. That means it forms a group. Is it clear? Is these 5 examples are clear? All these are based on matrix, right? 18, 19, 20, 21. Okay, these 4 examples. Is these 4 examples are clear? Is it clear, right? We'll move on to example number 22. Example number 22, right? I'm giving more examples. See, after that, it will be very easy for you. Example 22. Let X be any non-empty set. Let X be any non-empty set, right? So let X be any non-empty set. Let P of X be the let P of X be the power set of X. You know what's the power set? Set of all subsets. So if you have n elements, you can form 2 power n subsets. 9th standard, 10th standard level, right? Set of all subsets, empty set, and then one. For example, if you take 1, 2, 3, if you have a set with 3 elements, 1, 2, 3, what are the subsets? Empty set, full set, 1, 2 alone, 3 alone, 1, 2, 2, 3, 3, 1. So you will have 8 elements. So if you have n elements, you can form 2 power n subsets that you already know. So let X be any non-empty set. Let P of X be the power set of X. Then the set of all power set of X with respect to the symmetric difference. Here the operation is symmetric difference. Right? Operation is symmetric difference. If you have two set, you have to make operation between these two set by symmetric difference. Forms a group, right? In fact, it also forms an abelian group also. Right? Under symmetric difference. right? So what is A delta B? So whenever you have two set, how you perform A delta B? It is nothing but A minus B union B minus. This is the formula for difference, right? This set forms an abelian group with respect to the symmetric difference, right? You can easily prove this, right? See, you take any two element in power set of X, right? You need to show A star B is also in G. That is for closed. So what is A star B? A star B is A delta B, right? Because star here is delta. So what is A delta B? A minus B union B minus A. So this will also be in power set of X because A minus B, B minus A both are in P of X. So A minus B will be in P of X, B minus A will be in P of X, union of 2 will be in P of X because it consists of all those subsets only. So it will be in P of X. So it is closed. And again this associative also. So A delta B delta C is same as A delta B delta C, right? This is also true. And what about the ID element? What is the ID element for this set? What is the ID element for this set? Empty set will be the ID element, right? For A belongs to power set of X, there exists an empty set in power set of X such that if you perform A delta power set of X, right? That is, if you multiply A, this is a multiplication, it's symmetric difference. So if you perform operation with empty set, so what is A delta empty? So A minus empty union empty minus A, right? Because the definition A minus B union B minus A. So what about A minus empty set? It is A. Empty set union empty set minus A is A. See, from A, this is basic set operations. From A, you are removing empty set. It will be A again. From empty set, you are removing A. So it will be empty only. So A union empty is A. So you can see I'm operating A with empty set. I'm getting A again. So similarly, empty set union A is same as A. So that means for any A, empty set is our ideal element, right? And what about the inverse? For any A belongs to power set of X, same element is inverse, right? A inverse is same as A because if you perform A with A, right? If you perform A with A again, what you will have? So it is A minus A union A minus A, right? Because A delta B is A minus B union B minus A, and this is empty, this is empty, this is empty. That means you are performing with A, you are getting an ID element. That means inverse of A inverse is same as A. Whatever set you are taking, that is the inverse also. Because if you perform A with A again, you will get empty set. So that means A inverse is same as A. And also it is commutative also because A symmetric difference B is same as B symmetric A. So it forms an abelian group. Is it clear? See, this is the set operations, right? For example, if you take X to be 1, 2, 3, you will have 8 elements, right? You will have 8 elements. Empty set surely will be there. And also, for example, if you take a subset 1 comma 2, right? If you take a subset 1 comma 2, inverse is 1 comma 2 again because 1 comma 2 symmetric difference 1 comma 2, right? This is same as this is A, this is B. This is A, this is B. So A minus B will give you empty set because A minus B is A minus B. You know how to do difference of a set, right? And similarly, B minus A will give you empty set. So that means if you perform A with that again, you will get an empty set. So that means it is called self inverse. All the elements are self inverse. They are inverse to itself. It is called self inverse. Is it clear? So I'll move on to example number 23. Before that, I'll give you one definition. This is the second definition we are seeing now. Third definition. The first definition is definition of a group. Second is abelian group. Now we are seeing one more definition, order of a group. Right? The order of a group is nothing but number of elements in G. That's it, right? So number of elements in G is nothing but order of a group, right? So it is called O of G. Order of group. Note. G is infinite. Order of G is infinite. We are giving the first 13 examples are infinite group. And in the previous class, we have seen some examples like what is the order of cube roots of unity or order of Zn. It is 1 because it will have n elements. Order of order of cube roots of unity. Is 3. Order of 4th root of 20 will have. Order of nth root of 20 will be n. Right? Number of elements in the set is nothing but if it is finite only we can talk about order of a group. If it is infinite means if G is infinite, order of G is infinite. Right? Okay. So example number 23. Permutation or symmetric group. See, we will discuss this more in detail because we're going to study this separately as one topic. But as of now, I'm just going to tell the overview only. Permutation or symmetric group. Right? It is called Sn. Symmetric group of order n. What is Sn is nothing but Sn is all those bijection. All those bijection. Bijection means 1 to 1 plus on 2. All those bijections from S to S. Right? So you collect all those bijections from S to S. So all those 1 to 1 and on to mapping. Right? So Sn is all those n is a number of elements, right? If n is if n is 3, all those 1 to 1 map 1 to 1 onto mapping from a set of 3 element to a set of 3 element. Right? I'll give you an example. So S3. So S3 is all those 1 to 1 mapping from a set of 3 element to a set of 3 element. Right? It has to be 1 to 1 and on to. It is S3. So you always remember order of Sn is n factorial. Very, very important. So you can form n factorial mappings. can form n factorial bijections between a set from S to itself. S is, if you put n to be equal to 3, S is 3 elements. I'm taking 1 to 3, it can be ABC also. So I'm going to collect all those one-to-one mapping from a set of 3 element to a set of 3 element. One, two, and on to. See, usually you will have, so 1, 2, 3, 1, 2, 3. You will have 6 elements, right? Always remember order of Sn is n factorial. Here I'm putting n to be equal to 3. So that means it will be 3 factorial. 3 factorial is 6. So you'll have 6 elements here. So first is ID permutation, right? So 1 goes to 1, 2 goes to 2, 3 goes to 3. So it is ID, right? It is ID because you need to connect all those one to one onto mapping. The first is ID mapping. Every element is mapping to itself, right? Now second is 1, 2, 3, 1, 2. So we have 3 elements now, right? Okay. Okay, I'll write it in the single row so that it will be easy for you to understand, right? Presentation is very important for me. Okay. The first is ID permutation, right? See, now what I'm going to do is I'm going to move 1 to 2, 2 to 3, 3 to 1. So I'm just leaving one step. Just think of one step down. So here 1 goes to 1, 2 goes to 2, 3 goes to 3. It is called ID permutation. Right? This is 1 goes to 2, 2 goes to 3, 3 goes to 1. Now 2 steps down. 1 goes to 3, right? 2 goes to 1, 3 goes to 2. 2 steps down, right? Now other threes are, see, I'm going to fix 1. I'm going to fix 1 and I'm going to shift 2 and 3. Now I'm going to fix 2. I'm going to fix 2. I'm going to transform 1 and 3. Now I'm going to fix 3. I'm going to transform 1 and 2. So I'm assuming that everyone knows what is one to and on to, right? So on to means codomain has to be equal to range, right? Codomain has to be equal to range, or every element in the codomain should have a pre-image. That is the definition of on to. And for one to one, for each element, it has to be unique image, right? One element should not go to one element. Two elements should not go to a single image. Two elements should not go to a single image, right? Two elements should not go to single image, right? Okay, these are the 6 one to one and on to mapping that you can form if you have a set with 3 elements, right? See, I'm going to write down this mathematically, right? Because you don't want to write diagrams all the way, right? Very important stage. Just think of it. Very important. So you just write. This is the ID permutation, right? This is the ID permutation. See, you just write 1, 2, 3 in the top, right? Because you have 3 elements. Those 3 elements are 1, 2, 3 in the top. This is the notation for permutation. Now here you can see 1 goes to 2, 2 goes to 3, 3 goes to 1. Is it clear? This is the representation of this diagram. You should always write 1, 2, 3 in the top because we have S3. From this you can see 1 is going to 2, 2 is going to 3, 3 is going to 1. So if you out how you read like this, 1 goes to 2, 2 goes to 3, 3 goes to 1. So you in exam point of view they will give this only. So from this you need to understand that 1 goes to 2, 2 goes to 3, 3 goes to 1. Right? Yes. How you write this? 1 goes to 3, 2 goes to 1, 3 goes to 2. Right? Okay. 1 is fixed. That is 1 is going to 1. 2 goes to 3, 3 goes to 2. Here 2 is fixed, right? 2 is fixed. 1 goes to 3, 3 goes to 1. Here 3 is fixed. 1 goes to 2, 2 goes to 1. Is it clear? Is it clear? This is the representation of permutation. We can also represent in cycle also, right? We can also represent this in cycle also. In exam point of view, they will not represent like this because it is difficult to type this. They will represent in cycle. So they don't write this first row because first row is always 1, 2, 3, right? So to write cycle, this will be ID permutation only. They will write this as 2, 3, 1. That's it. If you want to write this as cycle, that means what? 2 goes to 3, 3 goes to 1, 1 goes to 2. You need to come in this order. 2 goes to 3, 3 goes to 1, 1 goes to 2. Here how you write? 3, 1, 2. So 3 goes to, sorry, 1 goes to 3, right? 1 goes to 3, 1, 3, 2, right? 1 goes to 3, 3 goes to 2, 2 goes to 1. You need to come in this order. This is the representation of cycle form. Here, if something is fixed, you should not write that in cycle. So here 2 and 3, that's it. If something is missing in the cycle means that number is fixed. Means that number is fixed. Here 2 is fixed. So 1, 3. This is 1, 2. Is it clear? See, both are same only. If some number is missing means you should assume that that number is fixed to itself in cycle form, right? In cycle representation. So therefore, S3 consists of 6 elements. What are those? S3 consists of 6 elements. One is ID, other is 231, 132, 23, 13, 12. These are the 6 elements. Is it clear? Is this slide is clear? Similarly, you can do for S4 also. So S4 consists of all those one-to and onto mapping from a set of 4 elements to a set of 4 elements. You can take any 4 elements, right? If you take 1, 2, 3, 4, you just find all one to onto mapping from 1, 2, 3, 4 to 1, 2, 3, 4. You will have 24 elements because order of Sn is n factorial. So that means you will have 4 factorial elements, right? So example is 4. See, what is the operation here? Operation here is composition. Operation here is composition, right? I will tell you how to make a binary operation between two elements. Okay, let us prove this is a group. After that, I'll give you example for S4. So we will show that this set is a group now, right? So S3 consists of I 1, 2, 3, 1, 3, 2, 1, 2, 2, 3, 1, 3. Right? These are the 6 elements. Now it is the binary operation is composition. Right? It is composition. I'll tell you. First is closed. So you take any two elements in S3, right? Let us take A to be equal to 1, 2, 3, B to be equal to 1, 2. Now what is A star B? A star B is composition 1, 2, 3, 1, 2. So how you find the product of two permutation? I'll tell you. See, you just write this in this form, right? If you write in this form, it will be easy for you to calculate. So what it means? 1 goes to 2, 2 goes to 3, 3 goes to 1. What it means? 3 is missing, 3 is fixed, 1 goes to 2, 2 goes to 1. So you need to find composition, right? So you can see 1 goes to 2, 2 goes to 1. You need to continue in this order. 1 goes to 2, 2 goes to 1. 2 goes to 3, 3 goes to 3. 3 goes to 1, 1 goes to 2. So what is permutation? So 1 is fixed here, 2, 3 is the permutation, and this belongs to S3. So whatever element you take, the product is 2, 3. So that is there here. So that means it is closed. I'm giving you one example of how to find the composition of two permutation. Is this clear? See, if you want to multiply two permutation, write this in normal representation form. So 1 goes to 2, 2 goes to 1. That means from 1 goes to 2, 2 goes to 1. If you have 3 means you need to continue for 3. For example, if you take A to be equal to 1, 2, 3, you take B to be equal to 1, 3, you take C to be equal to 2, 3. How you find A, B, C? That is how you product these two, 3. So write this in representation form. 1 goes to 2, 2 goes to 3, 3 goes to 1. Here 2 is fixed, 3, 1. Here 1 is fixed, 3, 2. So you need to write 1, 2, 3 the first. 1 goes to 2, 2 goes to 2, 2 goes to 3. 2 goes to 3, 3 goes to 1, 1 goes to 1. 3 goes to 1, 1 goes to 3, 3 goes to 2. So this is the representation 1, 3, 2. Is it clear? This is how to perform composition between the permutation. So it is closed, it is associative also. And a ID element is nothing but ID permutation. And also inverse also exists for each element. So how to find inverse, that I will let you know when we do permutation group separately, right? But it is not commutative. It is not commutative. Right? It is composition need not always be commutative. Right? It is not commutative. So it forms a group. Is it clear? The inverse, how to find inverse for each element, that I will let you know later when we do permutation group separately. Now similarly, you can construct S4 also. So what is order of S4? Order of S4 is 4 factorial. So we will have 24 elements in this set. You will have 24 elements in this set. Let me write down all those 24 elements. After I am writing 24 elements, you just practice that. Just a minute. So I write down the 24 elements of S4. So you will have ID permutation. One, 2, 3, 4, 5, 6. 6 plus 6, 12. Yes. So these are the 24 elements. See, this is a single permutation. It means 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3. So these are the 24 permutation you will have in S4. If my voice is clear, right? Yes. So we'll move on to some other examples. See, this means what? 1 goes to 2, 2 goes to 3, 3 goes to 4. For example, let me explain some examples. Let us take this 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. So here we have 2, 3. That means 1 and 4 are missing. That means 1 and 4 are fixed. 2 is going to 3, 3 is going to 2. This is the mapping for this. Right? For example, if you take 2, 3, 4, you take 2, 3, 4, 1 is missing. That means 1 is fixed. 2 goes to 3, 3 goes to 4, 4 goes to 2. Right? This means what? 1 goes to 4, 4 goes to 2, 2 goes to 3. Here 1 and 2 is missing. So 1 and 2 are fixed. 3 is going to 4, 4 is going to 3. So these are the 24 mappings that you can form with a set of 4 elements. So here 24 elements you will have. So in general, Sn forms a group, but it is not abelian group, right? Because composition need not be commutative. Is this clear? Permutation group is clear. So we will discuss more when we study permutation group separately. Okay, so last example, okay, many more examples. Okay, example 23, example 24. Klein 4 group. No. We will do dihedral group. title group Dn, right? So Dn is nothing but all those symmetries of a polygon. It is all those reflections and rotations. So Dn is all symmetries, all symmetries, that is reflections and rotations. Reflections plus rotations of a regular polygon. Right? Always remember order of Dn is always 2 times n. Right? Order of Dn is always 2 times n. You have 2n elements here. Let me give you an example. Let us take D4. Right? So what is D4? So D4 is all those reflections and rotations of a four-sided polygon. So regular polygon of n side. So four-side polygon is a square. So all those symmetries of a square is D4. What is D3? All the symmetries of a triangle. D5, all the symmetries of a polygon of 5 sides. Right? Similarly, Dn is all those symmetries of a n-sided polygon. Okay. So we will construct D4. So you will have 8 elements here because n is 4 here. So 2 into 4 is 8. So you will have 8 elements in D4. First is ID, right? First is ID. That is A, B, C, D. So I'm not rotating anything, right? I'm not rotating anything. Let us say this is our square, right? This is our square. I'm not rotating anything, right? So this remains as it is. So we have A, B, C, D. Now I'm going to rotate by 90-degree, right? I'm going to rotate by 90-degree. So I'm going to rotate by 90-degree. So if I rotate by 90-degree, right, in anti-clockwise direction, right, in anti-clockwise direction, you will have clockwise and anti-clockwise, no problem. So that means if I rotate 90-degree, um, one if I rotate 90-degree, one position will get shifted, right? So A will go here, A, B, C, D, right? So if I rotate by 90-degree, so A will come here. Everyone will shift to one position. So A B C D, A B C D. Let's rotate by 180-degree. Rotate this again 90-degree. So this A will go here. So A B C D. Rotate by another 90-degree. Rotation by 270. So this A will go here. If you rotate again, you will get ID again. Because if you rotate 90-degree again, you will get ID permutation again. ID rotation, right? So you will have 4 rotations. Always remember, rotations will be 2 pi by n. So n is 4 here. So 2 pi by 4 is 90-degree. So for every 90-degree, you need to rotate. If it is n is 3 means 2 pi by 3, right? Okay, these are the 4 rotations you have. And we're going to reflect now, right? I'm going to reflect now. See, first I'm going to rotate this horizontally. That is horizontal flip. So we have here, I'm going to rotate horizontally. Horizontal and then vertical. So 2 reflections. These are rotations. Reflection is horizontal one, vertical one. So if I do horizontal means, so I'm doing horizontal. So this will come here, this will go there, right? So AB will go there, DC will come here. Is it clear? If we do this here, AB will go there, DC will come down. Right? This is horizontal H. And I'm going to do vertical. I'm going to do vertical now with the help of ideal permutation only. So this will go this will come here. So if I do vertical shift, I do like this, CB will be here, DA will go there. Yes or no? If I do vertical, yes. Now diagonal reflection, right? So this diagonal and this diagonal. This is D, this is D dash. Let us fix this BD. Let us rotate this, right? So we have CA. And let us fix these two. Rotate this. Yeah, EB. Is it clear? So these are the symmetries of a square. So therefore, the elements of D4 are ID, R90, R180, R270. So we'll discuss this more again when we do dihedral group separately. Horizontal, vertical, two diagonals. So these are the 8 elements in D4. It will form a group. So in the diagram, you just have to, if you want to perform under again same operation composition only. So how you perform R90 into R180? Already you have R90, right? R180. You need to rotate R90 with 180. You need to do like that, right? This will form a group. Again, it is not abelian, only group only. So similarly, you can do for D3 and D4 also. See, 1, 2, 3, 4 means 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3. So 1, 2, 3, 4 means 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3. So you cannot write this in single cycle. 1 goes to 2, 2 is going to 1 again. So you need to close this cycle. 3, 4. You cannot write this in single cycle. This permutation you cannot write in single cycle. Because 1 goes to 2, 2 is coming to 1. It is closed. It is closed means you need to form a new cycle again. That is why we have a product of two cycle as one permutation. So is D4 is clear. Similarly, you can construct for D3 and D5 also in your own. So last two examples. After that, we'll be doing problems. That's it. Example 25 and 26. Line 4 group. Is called K4. So K4 consists of the element E, A, B, C. That the operations are denoted by, so all those are self-inverse, and AB will be equal to C, BC will be equal to A, AB will be equal to C. Forms an abelian group of order 4, right? So order of K4 is 4. Group of self-inverse. So every element is self-inverse. That is, the inverse for A is A. So inverse for A is A. That means what? A square is E. Inverse for B is B again. That means what? B square is E. Inverse for C is C again. That is mod. C square is E. That is what it is meaning. Every element is self-inverse. A group of self-inverse element. And if you want to multiply AB, answer will be C. This is the binary operation that you need to choose. Example 26. Quaternion group, Q8. Yeah, these two groups are very, very important, right? Just make a note of it, just put one box. Because we will be using this for many counter examples. Q4. So Q8 consists of 8 elements, less or minus 1, less or minus I, less or minus j, less or minus k, right? The operations are I square, j square, k square will be minus 1, ij will be k, ji will be minus k, jk will be I, kj will be minus I, ki will be j, ik will be minus j. That is, whenever you are multiplying those two elements, you need to follow this operation. So order of Q8 is, it has 8 elements, right? It is non-abelian group. You just put a big box to this. These are very important two groups, right? We will discuss this more in the upcoming classes when we do normal subgroups, cyclic groups, and so on. These 26 examples are clear. See, everything we're going to revolve this only from now on. All the higher concepts we're going to revolve from these 26 examples only. If you understand these 26 examples, then you can easily understand all the remaining concepts. We're going to revolve with this only, right? Okay. Just have a 2 minutes break. After that, we will do some problems. So problem will be like they will give a set, they will give a binary operation. You need to check whether it forms a group or not, right? Just have a 2 minutes break. Okay, so we'll do some problems now. Okay, this following set forms a group. The set I of integers with the binary operation A star B is equal to A plus B plus 1. Right, very simple. So here G is integers. So we have 0 plus or minus 1 plus or minus 2 and so on. Binary operation is A plus B plus 1. So whenever you are operating two elements, you need to make use of A plus B plus 1. Right? It is not usual addition. If it is usual addition means A star B is A plus B. But it is not usual addition. Whenever you are performing two elements, you need to make use of this operation. Okay. So first closure. So you take any two elements in G. Now what is A star B? A plus B plus 1. See, this belongs to AB belongs to G. G is integer. So A is integer, B is integer, 1 is also integer. So sum is again integer. So A star B belongs to Z. So therefore it is closed. You take any two elements, A star B should also be in G. G is integer. So A, B are integer, 1 is integer, sum is again integer. So it is closed. Associative. So for A comma B comma C belongs to G, G is integer here. A star B star C is same as A star B star C. So A star, now what is B star C? B plus C plus 1. What is A star B? A plus B plus 1 star C. Right? So A star B is A plus B plus 1. Now what is A star this? So this plus 1. Now what is this plus this star this? So A plus B plus 1 plus C plus 1. See, whenever you are operating two elements, first element plus second element plus 1. You are operating two elements here. First element plus second element plus 1. First element plus second element plus 1. So this is same as A plus B plus C plus 2. This is same as A plus B plus C plus 2. So they are associative. They are equal only. Now what about existence of identity? You need to find E element, right? So A star E is equal to A. This is the definition of ID, right? For A belongs to G, A star E is same as E star A is same as A. Now what is A star E? A plus E plus 1 is equal to A. So E plus 1 is 0. So E is equal to minus 1 is the ideal element. Right? So if you want to find ideal element, you need to write the definition and then apply the operation and then find E. For example, if you operate minus 1 with any element, for example, you operate 2 star minus 1. what you will have? You operate 2 star minus 1. A plus B plus 1. Right? So you are getting, you can see it is 2. So 2 star minus 1 is 2. That is, if you operate any element with minus 1, you will get that element again. That's what it means. A star is A means E has to be minus 1. If you perform 2 with minus 1, you are getting 2 again. What is 2 star minus 1? A plus B plus 1. So you are getting 2 again. So it means E is equal to minus 1 is the ideal element. Existence of inverse. So in problem point of view, if you want to find inverse identity, you need to apply the definition and then apply the binary operation which they have given. What is the definition of inverse? For A belongs to G, A star A inverse has to be E. Now E is minus 1. So what is A plus A inverse plus 1? E is minus 1. This implies A inverse is what? Minus 2 minus A, right? Minus, you just take these two elements that side. So minus 2 minus A is the inverse element for each element. For example, if you take A to be equal to 2, A inverse will be what? Minus 2 minus 2. So it will be minus 4. If you perform A and A inverse, A star A inverse, so it will be 2 minus 4 plus 1. So minus 2 plus 1, which is minus 1. So getting an ideal element, see. So A star A inverse is minus 1. So for any A, minus 2 minus A is the inverse element. Because if you perform A with minus 2 minus A, you will get minus 1, which is your ideal element. So minus 2 minus A is your ideal element. It is also commutative also. Right? Because A star B is same as B star A. A plus B plus 1 is same as B plus A plus 1. So it forms an abelian group. Yes, it forms an abelian group. Is it clear? This is what problem will be like in exam point of view. They will give a set. They will um, they will give a set. They will give binary operation. If you understand the single problem, then you can do all the remaining problems from your own. You need to apply the definition of ID and inverse to get the value of E and A inverse. Is this slide is clear? Okay, so we'll move on to second problem. See here the set is set of all rational numbers except 1. So they have removed 1 from the set. And the operation is A star B is A plus B minus AB. Here G is set of all rational numbers except 1. And whenever you are operating two element, you need to make use of A plus B minus AB. First flows for A comma B belongs to G. Now what is A star B? A plus B minus AB. See, this belongs to this is rational, this is rational, this is rational. So therefore, this has to be a rational. Output has to be rational. Sum of two rational is rational. Difference of two rational is rational. Okay. So therefore, it is closed. Associating for A comma B comma C belongs to G. G is Q minus 1. A star B star C is same as A star B star C. So what is A star B? A plus B minus AB star C. B star C is B plus C minus BC. Now what is this into this? So A plus B minus AB. This into this is A plus B minus AB. So you can simplify this. These two will be equal. Right? You can simplify these two sides. These two will be equal. Existence of identity or A belongs to G. They should exist. There exists E in G such that A star E is equal to A. What is A star E? A plus E minus AE is equal to A. AA will get cancelled. So E into 1 minus A is 0. Implies E is equal to 0 or 1 minus A is 0. E is 0 or A is 1. A1 is not possible, right? Because A belongs to G. But in G there is no 1. This is not possible. This is not possible because 1 doesn't belong to the group. Right? 1 doesn't belong to the group. That means E has to be 0. That means E has to be 0. So E is equal to 0 is your ideal element. For example, you take any two element, you take any element, you operate with 0. So it is 2 plus 0 minus 2 into 0. So you'll get 2 again. Right? So E is equal to 0 is the ideal element. Existence of inverse or A belongs to G. There exists A inverse in G such that A star A inverse has to give me E. So this will be A plus A inverse minus A inverse. E is 0. So if I take A inverse outside, we will have 1 minus A is equal to minus A. So A inverse is A divided by A minus 1. If I just take minus outside here, you will have A minus 1. So for A, so you can see A is not equal to 1 here. If A is equal to 1, inverse does not exist for here. But here 1 does not in our set. So that means denominator never be 0 because 1 is not in our set. That is why only they have given that except 1. If you add 1 means here also there is a problem, here also there is a problem. So for any A by A minus 1 is the inverse. For example, if you take 2, what is the inverse? 2 divided by 2 minus 1 is the inverse. Right? That means 2 into 1. What is 2 into 1? A plus B minus AB. A plus B minus AB. Take 2. 2 divided by, okay, 2 divided by 2 minus 1 is 2. Okay, sorry. So 2 plus 2 minus 4. So cancel getting 0. That means 0 is our ideal element, right? So it is correct only. And also, is it commutative? A plus B minus AB is same as it is commutative also. It is commutative also, right? So it forms an abelian group. Right? with respect to. See, this consists of all ordered pairs of real number, right? So every element is a pair here. Every element is not a single element. Every element is an ordered pair here. 1, 2, 3, 4, 5, 4. So every element is an ordered pair here, right? Okay. So G consists of all those ordered pairs such that this AB belongs to real number, right? Every element is a pair here. The operation is you take any two pair, you perform with this operation, right? Okay. Uh, so first it is closed. So you take any two pair. See, here it is not a single element, right? If you want, if single element is a pair here, so you take any two element. So let A comma B, C comma D. You take any two pair belongs to G, right? You do not take a single element. Single element is a pair here. Now you perform this operation A comma B star C comma D. So what is the operation? AC comma AD plus B. See, this is a real number. This is a real number. This will be a real number comma real number. So that means this also belongs to real number. Right? See, AB is a real number. That's it. So that means it is closed. For associative, you take any three pairs. Let us take P to be equal to A comma B. Let's take Q to be equal to C comma D. Let's take R to be equal to E comma F. Right? You just show P star Q star R is same as P star Q star R. You can easily do this, right? So P star, what is Q star R? Q star R is CE comma AD CF plus D, right? What is P star Q? AC comma BD plus B. See, you just have to perform this operation. AC comma AD plus B. Star R. R is E comma F. P is A comma B. So again you perform this, right? So ACE plus A into CF plus D plus B, right? ACE comma, right? ACE comma A into CF plus D plus B. Is it clear? Is it visible? See, you just have to multiply ACE this into this, comma, this into this plus B. This is the right? AC, AD plus B. Similarly, this will be ACE, comma, AC into F plus BD plus B. So these two will be equal. You can check it out. Right? This is F. So therefore, it is associative. Existence of identity for A belongs to G. There exists an element E in G. There exists an element E in G such that A star. See, here every element is a pair, right? Okay, let us take for A comma B belongs to G. There exists, let us say E comma E dash, because it's a pair, right? There exists E comma E dash in G. So A comma B, E comma E dash has to give me A comma B again, right? Usually you let A star E, but here every element is a pair. That is why I'm writing E comma E dash. So what about this AE comma AE dash AE dash plus B is equal to A comma B? Or no? AE AE comma AE dash plus B. AC comma AE plus B. So these two ordered pairs are equal. That means AE has to be A, AE dash plus B has to be B. That means E has to be 1. This means AE dash is equal to 0. E dash has to be 0. So 1 comma 0 is the ideal element. Right? E comma E dash. So if you operate any pair with 1 comma 0, you will get that pair again. So check it out, right? For example, you just take 2 comma 3. 2 comma 3 with 1 comma 0. Operate that with this binary operation, you will get 2 comma 3 again. Existence of inverse or A belongs to G. Okay, let us write A comma B. For A comma B belongs to G, there exists. Let us write A inverse as A inverse comma A dash inverse, right? In G, such that if you operate A comma B with A inverse comma A dash inverse, you have to get ID element which is 1 comma 0. Yes or no? Okay, we need to find A inverse A dash, and I just need to find a pair. Okay, if you want, you just write X comma Y, that is enough. They should, you just have to satisfy the definition, right? You just write some X comma Y, such that this into this has to give me 1 comma 0. That means this X comma Y is the inverse, right? So that means this is AX comma AY plus B. That means AX is equal to 1, AY plus B is 0. That means X is 1 by A, Y is minus B by A. So that means 1 by A minus B by A is the inverse for A comma B. So whatever element you A comma B, you just find 1 by A minus B by A. You operate these two, you will get 1 comma 0, which is your ID element. Is it clear? So 1 comma 0 is your ID element, and for any A comma B, for example, if you take 2 comma 3, 1 by 2 minus 3 by 2 is the inverse for that. If you take 2 comma 3, 1 by 2 minus 3 by 2 is the inverse. You can check it out that 2 by 2 comma 3 comma, sorry, 2 comma 3 star 1 by 2 comma minus 3 by 2 will give you 1 comma 0 with the help of this operation. It is also commutative also, right? It is also commutative also because A star this into this is it commutative? If you do C comma D and A, if you do C comma D with AB comma B, is it commutative? Okay, let us try to find C comma D comma A comma B. So this will be CA comma CB. No, it is not commutative. It is not commutative, right? This is not commutative because these two will give you this, but these two will give you other element. This is not commutative, right? Sorry. For example, if you take, it is not commutative. See, A comma B star C comma D will give you AC comma AD plus B. But C comma D star A comma B will give you CA comma CB plus D. They are not equal. Right? See, this first element is equal. First element is equal. But AD plus B is not same as CB plus D. Right? So it is not commutative. It forms a group, but it is not abelian group. Forms a group. Forms a group, but it is not abelian group. not abelian group. Okay, is it clear? Respect to composition of function. See, whenever you have a finite group, what I have said earlier, you need to put Cayley's table, right? If I made some mistake, just correct this, right? Correct it. Okay. We need to show that these four transformations forms an abelian group with respect to composition of function. You know how to composite two functions, right? Tension itself, you know how to composite two functions, F1 composite, F composite G. So, so you have a finite group. So that means you need to put the Cayley's table first. So you have F1, F2, F3, F4, F1, F2, F3, F4. So what is F1 composite F1? So F1 is ID, right? What is F1 composite F1 composite F1 is F1 of Z. So F1 of Z is Z. F1 of Z is Z again. So this acts as an ID element. So you will have F1, F2, F3, F4, F2, F3. Right? Now what is F2 composite F2? So it is F2 of Z. Now what is F2 of Z? F2 of Z is minus Z. What is F2 of minus Z? Minus of minus Z, which will give you Z, which is F1. Now F2 composite F3. This is F2 of F3 of Z. What is F3 of Z? F3 of Z is 1 by Z. So F2 of 1 by Z. F2 of Z is minus Z. F2 of this will be minus 1 by Z, which is F2 again. F2 composite F of F3 of Z is sorry F3 of Z is 1 by Z. Just a minute. Okay. So F2 composite F3 is F2. Now what is F2 composite F1? So it is F2 of F1 of Z. F2 of F1 of Z is Z. F2 of Z is minus Z, which is F2. F2, what is F2 F3? F2 of F3 of Z. F of Z is 1 by Z. 2 of 1 by Z is minus 1 minus 1 by. Okay, this is F4. Sorry. Minus 1 by Z is F4. Now what is F2 composite F2? F2 composite F2 is F1. What is F4? F2 F4, it has to be F3. F3 F2. Now what is F3 F2? F3 of F2 of Z. So F2 of Z is minus Z. So F3 of minus Z is minus 1 by Z. This is F4. See, it is very simple, right? So in F3 of Z, you need replace Z by minus Z. In F3 of Z, you replace Z by minus Z, which is F4. So this has to be F3. Now F3 F3. Now what is F3 F3? So F3 of Z. So F3 of Z is 1 by Z. So F3 of 1 by Z is Z. It will be 1 divided by 1 by Z, which is F1. So this has to be F2. This has to be F2. This has to be F1. This is the Taylor's table. After that, you can say it is closed associative. It is closed because uh, A star B belongs to G, or all A comma B belongs to G. Is associative. Composition is always associative. And what about ID element? F1 of Z is your ID element, right? F1 of Z is your ID element. And what about inverse? So what is inverse of F1? What is inverse of F2? What is inverse of F3? If it is finite means you need to write down separately. What is inverse of F1? It is F1. Inverse of F2 is F2 again. Inverse of F3 is F3. Inverse of F4 is F4. Every element is self-inverse. Always remember, if every element is self-inverse, that group will always be abelian group, right? And also it is abelian also. You can see it is commutative also. So it forms an abelian group with respect to. You just make a note of it. We will prove this later. If every element is self-inverse, self-inverse means inverse of that element is that itself. If every element is self-inverse, it is always abelian. See, you just compare this with Klein 4 group. This satisfies this group satisfies Klein 4 group. Yes or no? This group satisfies Klein 4 group. Yes or no? See, what is Klein 4 group? So Klein 4 group is the set of all inverse elements, right? Self-inverse element. Set of all inverse elements, and you can see every element A square, B square, C square is C. When you do AB, you will get C. When you get BC, you will get A. When you do AB, you get C. So this group satisfies all the properties of Klein 4 group. So this is an example of a Klein 4 group, right? It's a Klein 4 group. You can see F1, F2 is F1, F3 is sorry, F2, F3 is F4. So AB, AC is B. Something like that, right? So you just think of F1 as E. You just think of F1 as E, and you think this as ABC. So it satisfies the all the uh, binary operations of self Klein 4 group, right? See, in exam point of view, write it briefly. In exam point of view, write it briefly. Like it is closed. You take any two you take unity element A, B, and G. So it will be closed. You take any composition is always associative. You just write this by definition, right? I'm not written any definitions here, but in exam point of view, you need to write all those 5 definitions. Is it clear? So I'll give you one exercise problem based on the same concept. What are the set of what are the set of 6 transformations f1 of z is it abelian? It will not be abelian. You can check it out. If every element is self-inverse only, it will be abelian in composition, right? You similarly, you just have to you just find the K-list table f1, f2, f3, f4, f5, f6, f1, f2, f3, f4, f5, f6. For example, I'll do one example. For example, what is f4 composite f1? So it is f4 of f1 of z. So f1 of z is z. So what is f4 of z? It is z by z minus 1, which is f4. So f4 composite f1 is f4. Now what is f4 composite f5? So it is f4 of f5 of z. So f4 of f5 of z is 1 divided by 1 minus z. So in f4 of z, you have to replace z by 1 minus z. So f4 of z, so 1 divided by 1 minus z divided by 1 divided by 1 minus z minus 1. So in f4 of z, you have to replace z by 1 divided by 1 minus z. So this is 1 divided by 1 minus z into, this will be 1 minus z divided by 1 minus 1 plus z. This will be 1 divided by z. So 1 by z is f2. So f4 composite f5 is f2. So similarly, you fill the K-list table and you say that it forms a group. It will not be abelian, right? It will not be abelian. You similarly you find f5 composite f4. You see whether you are getting f2 or not, right? It will not be abelian. So take this exercise. So in this class, we have continued some examples based on groups, and then we have solved 5 problems as of now. So in the next class, we will be continuing more problems, and then we will be moving on to some theorems also is based on groups, right? That's it. So if you have any doubt, you can ask, or else we will wind up, right? Thank you. We'll see you in the next class. All the best.